All right, welcome everyone. If you've ever stared at a network science exam and felt like you were trying to read an alien language, well, you are in exactly the right place. Over the next few minutes, we're going to break down all the key concepts, walk through the tricky problems, and basically give you a master key to unlock that exam. So let's jump right in.
So, does this sheet of paper look a little familiar? Yeah, it can seem pretty intimidating at first glance with all its formulas and weird jargon. But trust me, by the time we're done here, you're not going to see this as some scary final boss. You're going to see it as a simple checklist of problems you know exactly how to solve.
So here's how we're going to tackle this. This is our game plan. First, we'll decode what these exam questions are actually asking. Then we'll start from square one with the fundamentals of graph theory. After that, we'll get into the big picture stuff with the major network models, learn how to actually navigate them with paths and searches, and then we'll wrap it all up with a killer summary and some revision strategy.
Okay, first things first. Let's dive into Section 1, Graph Theory Fundamentals. You know, every complex network, whether you're talking about Facebook or a map of all the airports in the world, they're all built from the same super simple parts. Once you get these building blocks, trust me, every single question on your exam gets a whole lot easier. Everything, and I mean everything, starts with the node. A node is just one of the individual dots or points in a network. It could be a person, an airport, a computer on the internet, a protein in a cell. It's basically the who or the what of the network. Simple as that.
Okay, so you've got your nodes. What connects them? That would be an edge, or sometimes people call it a link. This is the relationship. It's the friendship, the flight path, the phone call. And here's the bottom line. No edges, you don't have a network.
Okay, this is a super important one, so pay attention. Edges can have a direction or not. In an undirected graph, the relationship is mutual. Think about actors in a movie. If actor A worked with actor B, then B also worked with A. It's a two-way street. But in a directed graph, the edge has a direction, shown with an arrow. A phone call from me to you is a one-way edge. The exam loves testing this, asking which example is not undirected. The answer is always the phone call network, because that connection goes one way. So, you've got all these nodes. How do you figure out which ones are important? Well, the most basic way is to check its degree, which we usually write as the letter K. It's literally just counting the number of lines touching that dot. A node with a high degree is super connected. You could think of it as being really popular. Now, this brings us to a really cool idea that only applies to directed graphs with those one-way arrows. It's called a sink. Just imagine a customer feedback box at a store. It gets a ton of notes in, so it has a high in degree, but it never sends any messages out. Its out degree is 0. That makes it a sink, and that's a key definition you'll want to remember. Okay, let's zoom out a bit. Instead of just one node, what about the whole network? The average degree, which we write as K, tells us how crowded or connected the network is on average. Now, you might be looking at that formula and asking, why are we multiplying the number of links L by 2? Well, it's simple. Every single edge connects 2 nodes, so when you add up the degrees of all the nodes, you're naturally counting each edge twice. That's where the 2 comes from.
All right, let's put that formula to the test with a classic exam question. It asks about something called a complete graph. Now, a complete graph is special. It's a network where every single node is connected to every other node. It's the ultimate social network. So what do you think its average degree would be? Let's figure it out.
Okay, here's how we solve it step by step. The first piece of the puzzle we need is L, the total number of edges. For a complete graph, there's a handy formula for that. L equals n times n minus 1, all divided by 2. Now we just plug that into our average degree formula. We get K equals 2 times our big formula for L, all divided by n. And look what happens. The 2's cancel out, the n's cancel out, and you're left with this super clean, simple answer, n minus 1. And just like that, you've nailed a question that's almost guaranteed to be on the exam. Awesome. We've got the building blocks down. Now for the really fun part, the major network models. Think of these as the different blueprints that networks follow, which explain why they look and act the way they do. Okay, this table right here, this is basically your cheat sheet for network models. It compares the big ones you need to know, but the biggest, most important difference is that top row, the degree distribution. That just means how the connections are spread out. In a random network, you get a bell curve shape, but in a scale-free network, you get something totally different called a power law. First up, we've got the random network. Imagine you just throw a bunch of nodes on a page and start connecting them randomly with edges. As you keep adding more and more edges, something amazing happens. You hit a critical point where all of a sudden a giant connected chunk of the network just emerges. It's like a continent forming out of tiny islands. So the million-dollar question is, when does this magic happen? The exam will definitely ask this. It's when the average degree, K, hits exactly 1.
But, and this is a huge but, here's the twist. While that random model is neat, most of the networks you actually use every day, like the internet or your social network, they don't work like that at all. As this exam question points out, real-world networks are sparse and, most importantly, they are scale-free.
So what exactly is a scale-free network? Think of it like an airport map. You've got these massive hub airports like Atlanta or Chicago with tons of connections, and then thousands of smaller airports with just a few. Those big hubs are the defining feature. This leads to a power law distribution. Quick tip, to see if you have a power law, you have to plot it on a special graph called a log-log plot. It makes the curve into a straight line. And here's a fun piece of trivia that popped up on an exam. Network science was famously used to track down Saddam Hussein, but he himself was not the main hub of his own network. A classic misconception.
Okay, we've got the blueprints for our networks. Now let's talk about how to get around inside them. This section is all about paths, walks, and searches. Basically how we get from point A to point B.
You've really got to focus on this one because exams love to try and trip you up here. A Hamiltonian path is obsessed with the nodes. It has to visit every single node, but only once. An Eulerian path, on the other hand, couldn't care less about the nodes. It's all about the edges. It has to travel along every single edge just one time. And a self-avoiding path is just what it sounds like, a path that doesn't cross itself. I'll say it again because it's that important. Hamiltonian is for nodes. Eulerian is for edges.
So, want to see this in action? Let's go back in time to the problem that started this whole field of science, the 7 bridges of Königsberg. The townspeople wanted to know if they could take a walk that crossed every single bridge exactly once. Turns out, it was impossible. Why? And the answer is just so elegant. It's pure math. It was impossible. Because if you draw the city as a graph, you'll see it has 4 landmasses, or nodes, that have an odd number of bridges connected to them. Here's the rule you need to remember. An Eulerian path is only possible if there are either 0 or exactly 2 nodes with an odd degree. Königsberg had 4, so problem impossible.
Okay, but what if you don't care about visiting everything? What if you just want to find the fastest way to get from A to B in a network where every step is equal? For that, we use an amazing algorithm called breadth first search, or BFS. It's like dropping a pebble in a pond. It starts at your node, explores the first ripple of immediate neighbors, then explores the second ripple of their neighbors, and so on, layer by layer. This method guarantees you will find the shortest possible path.
So, what's the one thing the exam is definitely going to ask you about BFS? How fast it is. Its computational complexity is O(n plus L). Don't let the fancy letters scare you. All that means is that its runtime depends on the number of nodes, n, plus the number of links, L. In simple terms, it's incredibly efficient. That's why it's a go-to tool for finding shortest paths. Just remember O(n plus L).
Whew, we have covered a ton of ground. So for our last section, let's tie it all together with a quick summary and give you a solid strategy for exam day. This is your final checklist. Think of this slide as your last-minute revision checklist. These are the absolute must-knows. The formula for average degree, the shortcut for a complete graph, that magic number 1 for the random network tipping point, the fact that real networks are scale-free, the efficiency of BFS, O(n plus L, and of course, the difference between Hamiltonian, nodes, and Eulerian, edges. Seriously, if you know these 6 things, you're already in great shape. And finally, a few pro tips for when you're actually sitting in that exam hall. First, always check if the graph is directed or undirected. It changes everything. Before you start solving, just write down the definition of the term you're using. It shows the examiner you know your stuff. If you're stuck, just draw a tiny little graph with 3 or 4 nodes. It can make the problem so much clearer. And for multiple choice, start by crossing out the answers that are definitely wrong. It's a huge help. And that's it. We've cracked the code. You now have the fundamental tools, not just to pass your exam, but to start seeing the hidden networks that connect literally everything around you. So the only question left is, now that you have this new lens to see the world, what are you going to analyze first? You've got this. Good luck.